You know when you get a lab test back and you see that column labeled normal range? Have you ever stopped to wonder, where does that range actually come from? And how does a lab know it's the right normal for you? Well, today, we're going to pull back the curtain on the hidden but absolutely crucial science that makes your test results meaningful.
Right? We've all been there. You get the report, you scan down the page, you find your number, and you just check if it's inside those two goalposts. But here's a thought. What if those goalposts are in the wrong place? A normal range that was figured out in one part of the world might not be normal at all for your local community or for the specific machine your lab is using. So how do they get it right?
So here's our game plan. We're going to break it down into 5 parts. First, what normal even means. Then, how labs actually verify that normal. We'll get into the weeds with something called the 20 sample rule, figure out what happens when things don't line up, and finally, we'll talk about why this whole process matters so much for your health.
Okay, let's start with the absolute basics. Before a lab can check if a range is correct, we've got to understand what that normal range is supposed to be in the first place. So in the medical world, they don't really say normal range. The official term is a reference interval, or RI. And this is key. It's not some absolute rule of who's healthy and who's sick. It's more of a statistical snapshot. Scientists go out, they get a big group of healthy people, they test them for things the body makes naturally, and the RI is simply the range where the middle 95% of those results land. Which is kind of wild, right? It means that, by definition, 5% of perfectly healthy people will always have a result that's outside of normal.
And this is where the problem comes in. The company that makes a lab test, they provide a standard reference interval. But that interval was based on their test subjects and their machines. Your local lab could be serving a totally different population or using a slightly different testing method. It's like trying to use a map of one city to get around in another. A one-size-fits-all approach, it just doesn't fly.
So what's the solution? How does your lab make sure the range they're using is the right one for you? Well, the answer is a surprisingly simple but really elegant quality control process. It's called verification of reference intervals, or VRI. And this isn't just a nice-to-have thing. It is a strict regulatory requirement. In the US, for instance, rules like CLIA-88 flat-out mandate that every certified lab must prove that a manufacturer's range is right for their specific patients before they can start using it.
Now, it's really important to get this distinction. What we're talking about is verification. Think of it as a quick spot check. The lab is just confirming that an existing range is good to go. It's pretty routine and only needs about 20 local samples. On the flip side, you have establishment. That's a whole other beast. That's when a lab has to create a brand new range from the ground up. It's a massive project, a full-on study that needs 120 or even more healthy volunteers.
So we're going to focus on verification, that routine spot check. And the whole thing is built around a beautifully simple yet incredibly powerful rule. The experiment itself is really straightforward. First, the lab gets samples from at least 20 healthy people from their own community. Second, they run those samples exactly like they would any other day. Same machines, same process. And third, they just count. They literally count how many of those 20 results land outside the manufacturer's suggested range.
And that brings us to our first key number, 20. That's the minimum. You need samples from at least 20 healthy local people to do a meaningful check. You see, it's a bit of a sweet spot. It's a small enough number to be practical for any lab, but it's large enough to catch any big differences.
And that leads directly to our second key number, 2. Out of those 20 samples, no more than 2 are allowed to fall outside the proposed range. Think about it. If the range is supposed to cover 95% of people, you'd already expect 1 out of 20 to fall outside just by random chance. Allowing up to 2 gives a little buffer, but if you see 3 or more, yeah, that's a red flag.
This table lays out the whole decision tree. It's simple. If 0, 1, or 2 of your results are outliers, you get a pass. The range is verified. If you get 3 or more, you have to hit pause and do a retest with a whole new set of 20 samples. And if that second set also has 3 or more outside the range, then it's official. The range fails. It's not valid for this lab.
So what happens when it fails? Does the lab get into trouble? Is the test itself broken? Nope, not at all.
A failed verification isn't a sign of failure. It's actually a sign that the system is working perfectly. It's just a scientific signal that says, hey, listen, something about our local population or our method is consistently different from the original. It's not an error to be punished, it's a discovery that needs to be investigated.
And that investigation is serious business. The lab starts by reviewing all of its own procedures, just in case. If everything checks out there, they have to confirm the failure. And at that point, they have to do the big one, that full-blown 120-plus sample study to establish a brand new reference interval, one that's tailor-made for their specific community. This chart gives you a great visual of what a fail looks like. You can see the manufacturer's proposed range, and then you see the actual data from the local population. See how it's shifted? A whole bunch of local results are falling outside the proposed range. The VRI process worked. It caught this mismatch, and in doing so, it protected patients from having their results misinterpreted.
All right, let's tie it all together. Why should you, or I, or anyone, care about this nerdy, behind-the-scenes laboratory science?
Because this process is literally the bedrock of trustworthy medicine. It's a powerful little screening tool that makes sure when your doctor looks at your lab report, the normal they're comparing you against is actually relevant to you. It means huge decisions about your health are being made with accurate, validated data. It guarantees quality, and honestly, it gives all of us confidence in our results.
So the next time you look at a lab report and see that normal range, you'll know it's not just a set of arbitrary lines on a page. It's the product of a rigorous, scientific verification, a quiet but constant effort to make sure that your health data is, and always will be, truly meaningful.
So let me just ask you this straight up. Is your last sample haunting your next one? It sounds a little dramatic, I know, but that's really the core question we're trying to answer here. We're talking about a kind of invisible contamination that can have very, very real consequences on results.
To make this crystal clear, let's use an analogy you can almost taste. Imagine you've just had a spoonful of super spicy chili. That's our high concentration sample. Then, without washing the spoon, you go right in for a scoop of plain vanilla ice cream. That's our low concentration sample. You know that fiery kick you still get from the ice cream? That lingering heat? That, in a nutshell, is carryover. So let's bring that idea back into the lab. Carryover testing is the official procedure we use to measure that exact effect. We're checking to see if a tiny bit of residue from a very spicy or high concentration sample gets carried over by the instrument's probe and falsely bumps up the result of the next vanilla low concentration sample. And when we say concentration, we just mean the amount of the specific thing, the analyte, that we're trying to measure.
All right, so here's our game plan for today's investigation. First, we'll talk about why we even test for this stuff. Then we'll walk through the setup, which is pretty cool, crunch the numbers, talk about how we draw the line between good and bad, and finally deliver the verdict, pass or fail. So, first up, the contamination question. Why do we go through all this trouble? What's the fundamental reason for hunting down this carryover ghost? Well, this test really serves three main purposes. First, it lets us detect and, this is key, quantify any contamination. It gives us a hard number. Second, that number gives us a totally objective, black and white pass or fail decision. And third, that decision is absolutely vital for validating a new method or just making sure an instrument is running perfectly after it's been serviced. Okay, so how do you actually catch this ghost? You can't just test random samples. Now, you have to set a very specific, very clever trap. We're going to call it the 21 sample gauntlet. Now, this slide really shows you the precision we're talking about. The whole test uses 11 low concentration samples and 10 high concentration samples, and they have to be run in this exact sequence. I mean, perfect order. If you mess up the order, the whole experiment is invalid. This specific layout is designed on purpose to create these little moments where carryover is most likely to happen so we can catch it. So, once all 21 samples have been run through the machine, we've got our raw data. Now it's time to put on our detective hats and start the real analysis. The very first thing we do is sort the evidence. And here's the interesting part. We completely ignore the results from the high concentration samples. We only care about the low ones. And we split those into two groups. The first group is low values. These are low samples that came right after another low sample. The second and most important group is the high-low values, the low samples that came directly after a high one. You know, for all this setup, the math itself is surprisingly straightforward. It's just 3 steps. 1, you calculate the average or mean of that low group. 2, you calculate the average of the high-low group. And 3, you find the difference between those two averages. That difference, that's your carryover. It's really that simple.
And this formula right here says it all.
That single number we get, the carryover, represents the average little bump in concentration that a high sample gives to the low sample right after it. It's the ghost we've been hunting, and now we've given it a number.
So we've got our number. Let's say our carryover is 0.05. Is that good? Is it bad? Who knows? A number by itself is pretty meaningless. We need a threshold, a line in the sand to compare it against. And in the lab, this is called the error limit.
And this is where it gets really interesting, because labs have choices. They can use the automatic default setting, which is based on how much their own low results naturally vary. Or they can define their own limit, either as a percentage of the low value or as just a fixed absolute number. And the choice they make here is absolutely critical.
Which brings us to the climax of our whole story, the verdict. Let's walk through a quick example to see how that choice of error limit can completely flip the outcome. Okay, here's our evidence. After running our 21-sample gauntlet, we did the math. The average of our low samples is 1.00. The average of our high-low samples is 1.05. That gives us a final measured carryover of exactly 0.05. Now, for verdict number 1, let's say the lab uses the automatic rule. The error limit gets calculated as 3 times the standard deviation of their low results, which in this case comes out to 0.0474. So we compare our carryover 0.05 to that limit.
And, well, you can see it right there. Our measured carryover of 0.05 is higher than the acceptable limit of 0.0474. Under this rule, the verdict is clear. It's simple. The instrument fails the test.
But, hang on a second. What if the lab's procedure didn't use the automatic rule? What if they had defined a different and perfectly valid limit for themselves? Let's replay that scene for verdict number 2. This time, let's say the lab set its error limit at 5% of the low mean. Since our mean was 1.00, 5% of that is 0.05. Our measured carryover is still 0.05. And would you look at this? The pass/fail rule states that the carryover has to be less than or equal to the error limit. Our result, 0.05, is equal to the limit 0.05. It meets the criteria. So, with the exact same data, from the exact same instrument, but under a different rule, the verdict is now a pass. And this right here is the single most important thing to take away from our entire investigation. It's not just about the measurement you get, it's about the rules you use to judge it. The choice of how you define your error limit can literally determine whether you pass or fail.